In this video, we're going to talk about the reactions of alkenes and alkynes. And one thing to note that's specific to alkenes and alkynes in terms of reactions, or when you see an alkene or an alkyne in a reaction, is it's that carbon-carbon double bond or that carbon-carbon triple bond that's so highly reactive. And so when you look at these reactions, you got to think to yourself, it's that double or triple bond that's going to be breaking in these reactions. So when you look at all these reactions and you kind of look and go back to them after we've discussed them, you'll see that all of them have that same philosophy, that that double and triple bond gets broken in the process. So let's talk about the 4 types of reactions that we'll learn about in this video regarding alkenes and alkynes. And the first one is hydrogenation, and you'll see in the word hydrogenation, you see hydrogen. And what's cool about the names of these reactions is they kind of give away what's happening in the reaction a little bit. So in hydrogenation, we know hydrogen is going to play a role in this based on the name of the reaction. But we can take an alkene, and I'm just going to put a generic one because they're going to have that carbon-carbon double bond. And we can add some hydrogen in it for the hydrogenation reaction. In the presence of a catalyst, and you may remember a catalyst from earlier studies in chemistry, and this one's a palladium catalyst, which is just a metal. A catalyst doesn't get consumed in the reaction. It's not a product, it's not a reactant. It's just helps the reaction go a little quicker. But in the presence of a catalyst, what happens is that double bond gets broken, and so that carbon-carbon single bond then is there. Here are the 4 groups hanging on what was the original molecule, and then those 2 hydrogens make it so carbon now has 4 bonds. The hydrogens each have 1, and there is the product of the reaction. And again, I can take something simple like an ethene molecule. So there's the 4 groups hanging on that carbon-carbon double bond. I can add the hydrogen, and I'm going to change colors here so we can see it better. And remember, H2 is basically, these are the same thing. I just drew that one out more of a structural formula as opposed to a molecular formula that I did the first time. So those are the same thing. And then we can get a product here. That would be this. Notice that carbon-carbon double bond was broken, and the 2 new hydrogens are added on across that double bond to break the double bond. And we get that structure right there. Now we can do this with an alkyne as well. So I'll take the simplest alkyne, and that's ethyne, shown here on the left. We can add a hydrogen molecule to that. And here's what we would get if we did this reaction. One of the triple bonds would break. It would be left with a double bond. We'd have the original hydrogens that were on the ethyne molecule, and we add across that the new ones. And actually we could have this reaction go further, as you might guess, because now we have an alkene. Alkenes can react with more H2. So if we add more H2 to the process here, and we let this reaction go further, actually what I'll do is, so we can just really clearly see it, we'll make the next H2s, although these are the exact same molecules as the red ones, well, I'll make them purple this time so we can see where they're going. And we can see this was the hydrogens that were put on the first reaction, and then we'd have our new hydrogens that added across that double bond, broke that double bond to make it a single bond, and we have our new hydrogens on there now. So we started with an alkyne, we made an alkene, and eventually we made an alkane. So in this hydrogenation reaction, we can convert alkynes and alkenes into alkanes, is what actually happens here. And just to note, you might be wondering why, for instance, did I put the red ones up here at the top as opposed to the bottom? I could have put them at the bottom and had the black hydrogens at the top. That would have been fine. Same down here with these purple ones. These purple hydrogens I could have put at the bottom and put the red ones at the top and the black ones on the side. I could have done that as well. So it doesn't really matter where you put those hydrogens. What matters is that one hydrogen binds to one carbon and the other hydrogen binds to the other carbon. Let me show you the reaction just so this is clear in how the electrons move around to change those bonds. So I'll just show you that really quickly. Let's say we have let's take the carbon-carbon double bond, for instance, and so let's just make it the simplest one, just for to make it simple. We'll have an example at the end of this. And let's say we now have our new incoming hydrogen. And so here's our hydrogen molecule that's going to line up. What happens here, or the way you can at least think about it, is that these electrons move around. Remember, each of these lines connecting two atoms is 2 electrons. And so to make a new bond, we need 2 electrons to form. And so what happens here, essentially, is that these 2 electrons between the 2 hydrogens move to here. And these 2 electrons on one of these bonds between the carbons moves here. Right, and so what happens then, if I get my eraser out, is that these electrons disappear and show up right here. And then these electrons right here from the carbon-carbon double bond are lost, and those electrons show up right here. And so notice now in this situation, the hydrogens connected to the bottom, but notice they connect right next to each other because they're connecting in that way. I could have done and now notice there's a single bond between the 2 carbons, and we have new bonds. Each carbon has 4 bonds to them, and so we typically then would write this in this way. I'm not going to change colors here, but we kind of move those hydrogens around a little bit and put them like this. You know, we kind of swing these guys up just a little bit, just to kind of spread them out a little bit like we normally see them, because they do spread out a little bit. Because remember, an alkene structure is planar, so once these 2 new hydrogens bind, it becomes an alkane, which has tetrahedral structure. So the structure does change a little bit too. So we end up getting this structure, this alkane structure. Again, we could have bound the hydrogens. See if I can get rid of some of this. Actually, you know, we could have bound, I think you might be catching on to this, but just to show it, we can bind those hydrogens to the top where this electrons would come down, these 2 electrons would come up, and we get 2 new bonds right there. And notice now this time the new hydrogen's bound to the top side, not the bottom side. And when this reaction happens, it's pretty random. Sometimes it binds to the bottom, sometimes it binds to the top, and it just changes the location. But in the end, it doesn't, in this case, doesn't change what molecule is made in the end. So the next reaction is a halogenation reaction. And again, we'll take some generic alkene. It's going to have a carbon-carbon double bond, and that's where all the action is going to happen. And we're going to add a chloride molecule to this alkene. Now remember, halogens, we've talked about them before, are things like fluoride, bromide, chloride, and iodide are halogens. And so again, the name with the halogen in it kind of gives it away. halogen means one of those. And halogens don't exist as single atoms like hydrogen. They exist in nature as diatomic molecules, meaning it has two atoms. So Cl2, we can write that a little bit more in a structural way, not a molecular way. It would be that guy, ClCl. And this is going to react with that alkene the exact same way as the hydrogens did in the previous examples in hydrogenation reactions, except instead of hydrogens being added, chlorides are being added in this case, or fluorides or bromides or iodides. And so what's going to happen is the carbon-carbon double bond is going to break. The chlorides are going to add to one side of the double bond. And so we'll get whatever was attached to those two carbons, and I'm going to add the chloride to the top in this case. So again, it's the same thing where if we have a chloride binding to the alkene, one of the bonds, the electrons are going to move to here to form a bond. These electrons are going to move here to form a bond, and those bonds will disappear, and we'll be left with that structure. And again, those chlorides could bind to the top, or they could bind to the bottom, essentially. And we get that structure right there. This can also happen with alkynes. So we can have a carbon-carbon triple bond, and whatever is attached to those. We can add some halogen, like bromine, to it. And when we do that, again, we have a chloride triple bond, or a carbon triple bond. We have a bromine bound to a bromine, and again, that bond can move there, that bond can move there, and so in this case, we lose that bond between the two. We lose one bond between the two carbons, one bond between the two bromines, and we get that structure, and so we're left with an alkene structure. Whoops. I'm going to add it to the top here. Whatever was originally attached, and now we got bromines attached. And again, that could go through another reaction where we add another molecule of bromine, and we could get it down to an alkane structure where it would be a carbon single bonded, and we might have the bromine, the new bromines, the first round bromines, and then whatever was attached here and here on that carbons was originally attached here and here. Whatever that was would be still attached there. So let's talk about the third type of reaction, and that's hydrohalogenation. Again, the name gives away what it is. It's a hydrogen and a halogen. And so this would include the guys like hydrogen fluoride, hydrogen chloride, hydrogen bromide, and hydrogen iodide. Okay, and so these guys can also react, and they're going to react the exact same way. Notice I'm going to do hydrogen iodide, or HI, but let me remove that. And we can call it, actually I'm going to make it color-coded here. Let's see, let me get rid of that. And let's color-code this guy, because it's got a hydrogen on it. Let's do H bound to I, so it's got a bond in between those two. So notice, before we had two H's connected together, we've had two halogens connected together, like two bromines connected together, and now we have an H connected to an I. It's going to react in the exact same way that the other ones did. Notice here is our original molecule. Let's go ahead and make this an alkene, a simple alkene, and the HI is going to add across it. So here's our H connected to our I. These electrons will move between that hydrogen and that carbon. These electrons of the double bond will move between that carbon and that iodide, forming two new bonds, here and here. So we basically just move those electrons in this reaction. So let's now erase what was moved. And there's what we're going to end up with. And so we can draw that structure. So that's what it would be if we started with ethene. But this will work across any carbon-carbon double bond. And so just to finish out the structure above, just the generic structure, we would have a carbon single bonded to a carbon. We'd have things attached that were originally attached, whatever those may be. And then we'll have the new hydrogen and the new iodine. This also works with alkynes, although I'm not going to go through it this time. I think you can kind of look at the last couple of reactions we did with alkynes, and this would do the exact same thing. And the fourth major type of reaction of alkenes and alkynes is hydrohalogenation. Hydrohalogenation, again, the word kind of gives it away. I'm sorry, not hydrohalogenation, we already did that one. Hydration. And hydration, just hearing that word, kind of, we already know what that kind of means. We've heard of hydration before. Anytime you're hydrating yourself, you're adding water, or H2O. Now, H2O can be written that way too. Notice that's two H's and an O. But the way I like to do hydration reactions, remember when water, you might remember from Gen Chem, if you have water, it likes to ionize a little bit and become H plus OH minus, right? It likes to break apart. And when it breaks apart, it doesn't break apart that often, but when it does, it breaks apart like that. And so you break it into two pieces. So although there's 3 atoms this time, which in the previous 3 reactions we only had 2 atoms in the reactant with the alkene or alkyne, in this one we have 3 atoms, but they break apart into 2 pieces, and the 2 pieces are the H and the OH. And so when we add this across a double bond, we'll add H to one carbon, and we'll add the OH to the other carbon. And we don't have to worry about those charges because they'll be bonded again in a way they like to be bonded. And when we see OH, remember just in molecular ways, that's O connected to H like that. So here we are. Here's our reaction of an alkene with a water molecule. So we're going to do a hydration reaction. And when we do that, we're going to break apart that carbon-carbon double bond. And we're going to add a hydrogen to one side of that to one of the carbons of the double that was originally part of the double bond, and one to OH. And so we form that. So we're going to learn later that this is an alcohol because it has that OH group on it. And we'll learn that later next week or maybe Friday. On this one, this is an alkene. So this hydration reaction is a great reaction to convert alkenes into alcohols. Now, something to point out about these reactions. In the first 2 reactions, the 2 atoms being added across the double bond or the triple bond were the same. Remember, the first one was hydrogenation reaction. The 2 atoms being added were an H and an H, so they were the same. In the second one, in the halogenation reactions, it was this halogens, like for instance, it might be a chloride and a chloride or a bromide and a bromide, but nonetheless the 2 atoms were identical. In the last 2 reactions, the 2 atoms were not the same. In hydrohalogenation, notice one was a hydrogen and the other was a halogen, like chloride. And so notice they're not the same. And in the hydration reaction, the same. One was a hydrogen and one was a hydroxyl group. So they're not the same. These 2 present a little bit different problem when we start to add those across double and triple bonds. And let me show you an example of what I mean by that. So let's take one of those, and we're going to go ahead and add, we're going to take a alkyne, and we're going to add across that alkyne, actually let me start this over. Let me try to stay consistent with my colors. Let's take the simplest alkyne, we'll take that one, and we're going to add a hydrohalogen like HCl. And so we'll look at this. A couple of things to note is, and I'm going to come down here to the bottom for just a moment and redraw this and show you how things get added. We've already talked about how hydrogen will add to one carbon and the chloride will add to the other. So we could just go quickly and just take our H and our Cl. The electrons will move and we'll get this structure right here. Right? That's a possibility. Correct? But also remember that these atoms that we're signifying with these C's, H's, Cl's, right? We're signifying that they're not really letters in reality, right? They're like spheres. And so remember that they can also add in this way. I'm going to do some erasing here. We're going to do this again. But it's also possible, let me add my triple bond back, but it's also possible that the hydrogen chloride adds in this way, or the hydrogen adds to the other carbon and the chloride adds to the other one, right? And so again, we still have the same thing happening. We have this bond going there, that bond going there, and we get this structure. Now notice in this one, the carbon added to the other, the chloride added to the other carbon, so they kind of switched. So you got to remember that when you have adding a molecule across that double or triple bond, if they are different, there's really two ways it can add. So we have to keep that in mind. And let me show you how that would affect this reaction. So let's just do this reaction. Again, there's two possible answers here, right? There's one in which we add the chlorine to the first carbon. So there's it added to the first carbon. Right, and I didn't color code it, but I could have. But I think you see where it was added. And there it is added to the second one, right? So it made what looks like two different products. Well, it turns out it didn't really make two different products, because if we name these both would name the same thing, so it's the same molecule. It didn't change anything, right? Because both of them are, because they're the ene family, there's two carbons, and the chloride's on the first carbon, so it would be, well, the double bond's on the first carbon, and then we have one chloro, one ethene, right? And they're both the same, because this on the bottom one, this would be the first carbon, that would be the second one. On this one, that would be the first carbon, that would be the second one. Same molecule. So in the end, it didn't make a difference. But on some molecules, it will make a difference, that it will change the name of the molecule, so it'll change the product. In this case, it turns out it didn't make two products. It doesn't matter which way it adds, it makes the same molecule. But let's continue. Remember, this molecule can add another hydrogen chloride across that double bond. And what products could we get? Well, now there are two products we could get. Let me erase this guy, get rid of him. So there are two molecules we could get. So I'm going to rewrite the product of the alkene product. The alkene product was that we have written up there. It looks like this now. And now let's go ahead and add the HCl to it. Now the HCl could add in one of two ways. I'm going to write it below this time, but I could write it above just as easily. It could add like this, which would put the chloride on the second carbon, right? So we'd have one chloride on one carbon and one chloride on the other carbon. But I could also add it this way, where now this would put two chlorides on one carbon and no chlorides on the other carbon. So we have two possible products. Let me show you just to bring this all home. These electrons would move here, these electrons would move here. We'd have new bonds there. I'll erase the old bonds and the arrows just to clean it up. and we get that molecule. And this molecule would be, 1,1-dichloroethane. And the other molecule would be whoops, nope, that's not what it would be. If the chlorine added to the other carbon, it would be this molecule, which would be, if I can get it all in here, this would be 1,2-dichloroethane. Sorry, my handwriting's a little messy there. So when you start to react these double bonds, there's times at which the products, there could be multiple different products. So we start getting mixtures of products, not just a homogeneous single product, but multiple potential products. So keep that in mind as you work with alkenes and alkynes. So go ahead and we're going to use now a molecule, and we're going to do a reaction here. Go ahead and try to figure out what the potential product or products are of this reaction. And then when you're done, come on back and we'll talk about it. So the first thing you do is try to figure out what type of reaction this is that we're running here, what molecules are involved. And I can see over here on the left that this is an alkene. And so I think back and I know that there's 4 reactions that we're learning about alkenes. If this was an alkane, then this has got to be like a halogenation reaction. You're looking for a halogenation reaction or a combustion reaction because that's all we learned. But this is an alkene, so we know that there's 4 different types of reactions that were possible. One is hydrogenation. That would be the other molecule besides the alkene would be a H2. And I can see here this is not H2, so it's not a hydrogenation reaction. We also learned halogenation reaction. Well, there's definitely no halogen as the other reactant, and so it's not a halogen. Is it a hydrohalogenation reaction like that? Nope, it's not a hydrohalogenation because, again, I don't see a halogen up in there, so it's not that. The other one we learned about was hydration reaction, and that's what this is. We can see a molecule of water there, and so we have learned now that this is we figured out now that this is a hydration reaction of an alkene. And so now we have our alkene, and because it's an alkene, we also know that what's highly reactive is this carbon-carbon double bond. So that's where all the action is going to happen. It's not going to happen out in here where you see all this stuff, because when you see that double carbon-carbon double bond and carbon-carbon triple bond, you got to focus in on that a little bit. And so if we want to write this guy out a little bit, we can write him out as this, because these are the 2 pieces that we're going to add across that double bond. We have an H and we have an OH. The question is, where do they go? I could react this in this way, where the OH will connect to this carbon and the H will connect to this carbon, right? Or I could write it the other way, or the molecule could interact or attack in the other way, where we have it the other way around, where the OH attaches over here and the H attaches over here. Of course, when that happens, the carbon-carbon double bond will disappear. I have not shown that. So notice now there's potentially 2 different products. So I'm going to go ahead and do it both ways and potentially get the 2 different products. Now they might end up being the same, but we'll go ahead and double check all that. So let's go ahead and add the water molecule across the double bond. And for simplicity's sake, I'm going to kind of remove the hydrogens that are in the alkene structure, just so we can just see the carbon-carbon backbone. So I notice this is a 2. This molecule here is an alkene. So it ends in -ene. It has 5 carbons. It's pent, and carbon 2 is where the double bond is, so it's 2-pentene. So 1, 2, 3, 4, 5. It had a double bond right there, so I'm just straightening it out a little bit. Again, that just helps me see everything. And now I can go ahead and add the water molecule. Actually, what I'm going to do, I won't do it that way. That might be confusing. What I'll do is I'm going to go up here and just add it up here and then rewrite it. So I could have an HOH is one possibility where the two bonds are there and this one disappears, right? And so now I can name the new product. Now I'll put the product, the reactant was in black, I'll write the product in red. So what do we have here? Now we have a alkane structure. Actually, it's not even an alkane, it's an alcohol, so we haven't learned alcohols yet. So we'll put notice the hydroxyl group, the OH, is on the second carbon. Okay, so it looks like we have a hydroxyl group on the second carbon. Notice that's one product. If we do it the other way, so one product would have hydroxyl on second carbon, right, of this what looks like an alkane with a hydroxyl group on it. Again, we'll learn how to name that later on, but that's one product you could draw. Let's remove this, and we could put the hydrogen here, and the OH here is a possibility. That puts the hydroxyl group on the third carbon. And it doesn't matter which way you number that carbon chain, that OH is going to be on the third carbon. And so you have two different products here. One where the hydroxyl group is on the second carbon, and one where it's on the third carbon. Because again, when the double bond or triple bond is broken, the two groups could add to either carbon, and that's random which way it has some randomness to it. It's just how do they interact with each other.